We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
I feel the liftoff. The clock has started. Roger. Godspeed, John Glenn.
Roger, 0G, and I feel fine.
This is a new and strange environment at first. This suddenly finding yourself in orbit.
We have a liftoff, 32 minutes past the hour. Liftoff on Apollo 11. Houston, Tranquility Base here. The Eagle has landed.
Hello and welcome. This is Michael Annis, and you're listening to episode 13 of the Space Rocket History Podcast. And now, Explorer 1, Juno 1. You may recall from episode 12, Vanguard Test Vehicle 3, America's first attempt at launching a satellite ended in disaster on December 6, 1957. This meant that General Medeiros, William Pickering, and Wernher von Braun would get their chance to launch the first U.S. satellite. General Medeiros and von Braun had promised it could be launched in 90 days. They were given until February 1st, 1958 to make their attempt. After that, there would be another attempt by the Vanguard team. General Medeiros and von Braun were willing to make a 90-day promise because their attempt would essentially be a repeat of their 1956 launch, except this time there would be fuel in the fourth stage and a real satellite instead of a dummy payload. Also, William Pickering and Ernst Stuhlinger, conscious of the odds against a successful Vanguard mission, had persuaded James Van Allen of the University of Iowa to make the package of scientific instruments being ready for Vanguard compatible with Explorer 1's Jupiter-C launch vehicle. And finally, General Medeiros had managed to quietly store 2 Jupiter-C rockets in an advanced state of readiness in case a satellite launch was ever approved, so the parts and the pieces to make an attempt were readily available. Von Braun's team went into overdrive and had Juno 1 ready for launch by late January 1958. Working closely together, the Army Ballistic Missile Agency, that's ABMA, and JPL completed the job of modifying the Jupiter-C and building the Explorer 1 in just 84 days. Now some important specifications that are relevant to the story. First, the launch vehicle specs. The Jupiter-C rocket was originally developed to test the ablative reentry nose cone of the Jupiter Intermediate Range Ballistic Missile. However, its satellite launching capabilities were recognized at the time it was designed. The launch vehicle consisted of a modified Redstone ballistic missile topped by 3 solid propellant upper stages. The tankage of the Redstone was lengthened by 8 feet to provide additional propellant. The instrument compartment was also smaller and lighter than the Redstones. The launch vehicle stood 69.5 feet tall, or 21.1 meters, had a diameter of 5.8 feet, or 1.78 meters. The weight was 64,000 pounds, or 29,000 kilograms. The first stage had a Rocketdyne A7 engine that could deliver 83,000 pounds of thrust, which was about 7% of the Soviet R7 and almost 4 times as much as the Vanguard first stage. Burn time was 155 seconds. The propellant was liquid oxygen as an oxidizer, and hydine, which is 60% unsymmetrical dimethylhydrazine and 40% diethylentriamine. The upper stages of the rocket were all solid-fueled. They were arranged in an interesting manner. The second and third stage were mounted in a cluster inside of a tub, clearly visible on top of the vehicle, and the fourth stage was on top of the tub itself. If you're having trouble picturing this, there are some photos on the website, spacerockethistory.com. The second stage was an outer ring of 11 JPL scaled-down Sargent rocket engines, capable of delivering a thrust of 16,500 pounds for 6.5 seconds. The third stage was a cluster of 3 JPL scaled-down Sergeant rockets capable of delivering a thrust of 5,400 pounds and a burn time of 6.5 seconds. The second and third stage were held in position by bulkheads and rings and were surrounded by a cylindrical outer shell. The webbed base plate of the shell rested on a ball-bearing shaft mounted on the first stage instrument section. 2 electric motors spun the tub at a rate varying from 450 to 750 RPMs to compensate for thrust imbalance when the cluster motors fired. The rate of spin was varied by a programmer so that it would not couple with the changing resonant frequency of the first stage during flight. The fourth stage consisted of 1 JPL scaled-down Sergeant rocket. Thrust capability was 5,400 pounds and burn time 6.5 seconds. The upper stage was spun up just before launch. During first stage flight, the vehicle was guided by a gyro-controlled autopilot controlling both air vanes and jet vanes on the first stage by means of servos. The vehicle was launched vertically from a simple steel launch pad. The vehicle was programmed so that it was traveling at an angle of 40 degrees from the horizon at burnout of the first stage. At first stage burnout, explosive bolts were fired and springs separated the instrument section from the first stage tankage. The instrument section and the spinning tub were slowly tipped to a horizontal position by means of 4 air jets located on the base of the instrument section. When the apex of the vertical flight was reached after a coasting time of 247 seconds, a radio signal from the ground ignited the 11 rocket cluster of the second stage, which separated the tub from the instrument section. The third and fourth stage were fired in turn to boost the satellite and fourth stage to an orbital velocity of 18,000 miles per hour. When used as a satellite launching vehicle, the Jupiter C is sometimes referred to as Juno 1. And now the satellite specs. The 14-kilogram, 31-pound satellite was located in the top section of the fourth stage of the rocket. It was cylindrical, about 2 meters in length or 80 inches in length, and about 6 inches in diameter or 0.152 meters. 4 whip antennas were mounted symmetrically around the midsection of the rocket. Explorer 1 was designed and built by the Jet Propulsion Laboratory of the California Institute of Technology under the direction of Dr. William H. Pickering. The satellite instrumentation of Explorer 1 was designed and built by Dr. James Van Allen of the State University of Iowa. The 5-kilogram, 10.6-pound instrumentation package was mounted inside the forward section of the rocket. The instrumentation package included a cosmic ray detector, an internal temperature sensor, 3 external temperature sensors, a nose cone temperature sensor, a micrometeorite impact microphone, and a ring of micrometeorite erosion gauges. Data from these instruments were transmitted to the ground by a 60 milliwatt transmitter operating on 108.03 megacycles and a 10 milliwatt transmitter operating on 108 megacycles. Transmitting antennas consisted of 2 fiberglass slot antennas in the body of the satellite itself and 4 flexible whips from a turnstile antenna. The rotation of the satellite about its long axis kept the flexible whips extended. The external skin of the instrument section was painted in alternative stripes of white and dark green to provide passive temperature control of the satellite. The proportion of the light and dark strips were determined by studies of shadow-sunlight intervals based on firing time, trajectory, orbit, and inclination. Electrical power was provided by a nickel-cadmium chemical battery that made up about 40% of the payload's weight. These provided power that operated the high-power transmitter for 31 days and the low-power transmitter for 105 days. Because of the limited space available and the requirements for low weight, the Explorer 1 instrumentation was designed and built with simplicity and high reliability in mind. Now the sequence of events leading up to the launch. Keep in mind the deadline for the launch was February 1st, 1958. On December 20th, 1957, the Redstone first stage of the Juno 1 launch vehicle arrived at Cape Canaveral. It was shipped in 2 pieces aboard a Douglas C-124 aircraft. The first stage hardware was transported under strict secrecy to Hangar D in the Cape Canaveral industrial area for pre-launch processing. On January 15, 1958, the Juno first stage was trucked to the Cape Canaveral launch pad number 26A. The next day, January 16th, Juno 1 first stage was hoisted to its vertical position atop a 4-legged steel firing table. Azimuth vertical alignments were checked and electrical and pneumatic connections were made and power plant tests were begun. On January 17th, tests of the Juno 1 first stage power plant were completed. On January 20th, control and pressurization tests of the Juno first stage were performed. On January 21st, radio frequencies linking the Juno 1 to the Cape Canaveral Range Safety Office and gyroscopic guidance systems were checked. On January 23rd, an overall test of Juno 1's first stage components was completed, clearing the vehicle for launch. On January 24th, under strict security and the cover of darkness, the cluster Juno 1 Baby Sergeant upper stage rockets were transported to launch pad 26A and hoisted to their position atop the Redstone first stage. The work was performed inside the closed sections of the launch gantry to aid in security. On January 25th, safety wiring was installed aboard the Juno 1 rocket as preparations were made for a countdown dress rehearsal. On January 27th, as preparations proceeded at the launch pad, the veil of secrecy gradually lifted from the project. Newspaper reporters were notified of the impending launch. A countdown rehearsal was conducted in preparation for the first launch attempt, which would be 2 days later. Everything went smoothly. On January 28th, weather forecasters predicted unacceptably strong high-altitude winds during the planned launch attempt for January 29th. On January 29th, the New York Times ran an advance story sketching a fairly detailed overview of the flight plan. The Chamber of Commerce in neighboring Cocoa Beach, Florida, printed up 5,000 moon flight tickets as a publicity gag. Technically, the launch was still supposedly classified. Due to the prediction for unacceptable high-altitude winds, the ABMA called a scrub of their first scheduled satellite launch attempt. The scrub was issued in the morning prior to the start of the countdown. On January 30th, high-altitude winds were considered marginal early in the day, but the countdown was begun on schedule. However, the ABMA was forced to call another scrub due to unacceptable high-altitude winds. The scrub was not called until about 1 hour prior to the planned launch time of 10:30 p.m. On January 31st, 1 day before the deadline, at 8:30 p.m., technicians began fueling the Jupiter-C rocket's massive first stage. The rocket's destruct system was armed. Platforms surrounding the vehicle were removed, and the gantry was rolled backwards on its tracks. Floodlights were turned on, and the missile stood like a great finger pointing to heaven, stark white and alone on its launching pad. More than 24 film and still cameras units clustered outdoors at one vantage point. The Los Angeles Times called it the most elaborate array of cameras that had ever been assembled for a single news event up to that point. The countdown was halted when the team noticed what appeared to be a leak at the bottom of the rocket. One technician bravely ran over and looked up underneath the rocket's nozzle. The liquid was an old spill left over from loading the hydrogen peroxide used to drive the rocket engine's turbopumps. This caused a minor delay in the scheduled launch. Instead of 10:30 p.m., it would be 10:48 p.m. When 10:48 p.m. finally came, there was no further reason to delay. On a signal from General Medeiros, who was in the blockhouse just 100 yards from the launch pad, the head of the launch crew said, "Firing command." A member of his team pulled out a metal ring on the console and gave it a twist. An electric motor at the top of the first stage kicked into life, spinning the upper stages around and around. 13 seconds later, the massive engine on the Jupiter C's first stage ignited. It built up thrust for 3 seconds, gradually climbing into the night sky. Now here's an audio clip of the countdown.
After the firing signal is given, it will take almost 16 seconds for the vehicle to take off. Pressurization will be started at X plus 3 seconds. At X plus 14 seconds, ignition will begin. Thrust buildup will continue until liftoff at about X plus 16 seconds.
5, 4, 3, 2, 1. Firing command. Firing command. Firing command.
The team in the blockhouse listened with rapt attention to a whining signal transmitted from the satellite, until it abruptly stopped. "I've lost signal," Medeiros yelled. The team phoned a large hangar 3 miles away, where most of the tracking and support team was based. 40 seconds later, Medeiros was told that ground stations still had a signal. 2 minutes and 37 seconds after launch, the first stage burned out as the rocket sped southeast toward the Caribbean. Explosive bolts fired and springs pushed the rocket upper section out of the way from the spent booster. Jets of compressed air nudged the remaining rocket from its flight angle of 40 degrees skyward into a horizontal path pointing toward the horizon. The next step in the launch sequence called for a key piece of human judgment. In order for the satellite to reach orbit, it was critical for the second stage to fire precisely when the vehicle reached the peak of its flight path, with the rocket parallel to the Earth's surface. The responsibility for this task fell on Ernst Stuhlinger, one of von Braun's group directors who came with him to the U.S. from Germany. He was stationed in a hangar a few miles from the launch pad. Stuhlinger consulted telemetry from an onboard accelerometer, along with radar and radio data, and used a special analog computer that he had designed to work this out. 4 minutes and 20 seconds after the first stage had burned out, Ernst sent a signal commanding the first cluster of JPL's upper stages to fire. Firing of the third and fourth stages was controlled by timers. Post-launch analysis revealed that Stuhlinger's timing was impeccable, and he has since been known by his colleagues as the man with the golden finger. As the rocket disappeared from view, back in the blockhouse, General Medeiros' attention shifted to JPL's Al Hibbs. It was Hibbs' job to synthesize all the information coming in about the progress of the launch and to make a statement about the satellite's predicted state. Being a good engineer, Hibbs spoke not in black and white certainties, but in the language of statistics. A half hour after the launch, Hibbs told General Medeiros that he could conclude with 95% confidence that there was a 60% probability the satellite was in orbit. "Don't give me any of that probability crap, Hibbs," Medeiros snapped. "Is the thing up there or not?" Hibbs replied, "It's up." But for some time it wasn't really clear. The greatest proof positive of the satellite's fate would be a steady beeping of its radio signal as it passed over ground stations. In those days, there was a ragtag collection of outposts, far different from today's multi-continent deep space network. In 1958, the first ground station after Cape Canaveral was a Navy facility on the island of Antigua in the eastern Caribbean. Following that, the satellite would pass over British bases in Nigeria and Singapore, and finally it would reach a temporary ground station that JPL had set up in Earthquake Valley, northeast of San Diego, California. Then there would be nothing until once again it flew over the launch site in Florida. In another twist to the story of inter-service rivalries, the Navy allowed JPL's tracking team to place a radio receiver at its base on Antigua, but JPL could not deploy its own antenna. It would have to use an existing one at the Navy site, and no opportunity was provided to test it. Shortly before launch, a switch was thrown to connect the antenna to JPL's receiver. The switch was badly weathered, and as a result, the antenna did not work. No signal was received from Antigua. As for Nigeria and Singapore, the receiving equipment there worked well enough, but in that age before communication satellites and the global internet, there was no telephone or telegraph link from those outposts to the United States. So the first definitive chance to hear from the satellite in orbit was when it would pass over California. In addition to the station in Earthquake Valley, a backup receiver was established at an amateur radio club in Temple City, a few miles southeast of JPL in Pasadena. Exactly when the California stations would pick up the satellite was a matter of conjecture. The team estimated it would fly over the west coast around 12:30 a.m. Eastern Time, about an hour and 3/4 after launch. Another reason for tension was that in Washington, Pickering, von Braun, and Van Allen would soon be on their way through a rainy night from the Pentagon to the National Academy of Sciences, where they would be expected to pronounce the launch a success or failure. Pickering kept a phone line open for the word from California. At 12:30 a.m. in Washington, spirits were deflated when there was no signal. Von Braun recalled later, quote, "We were miserable. The Explorer had never really gone into orbit," end quote. Someone walked over to Pickering and said, quote, "Well, better luck next time, Bill. I guess you didn't quite make it." End quote. Pickering responded quietly, "I'll wait till my boys tell me that." At approximately 12:48 a.m. Eastern Standard Time, the first listening stations began reporting that they had received signals from the Explorer satellite. The first station to confirm the signal was the San Gabriel Valley Amateur Radio Club near Pasadena, California. However, ABMA officials were waiting for confirmation from Goldstone Radio Tracking Station in Earthquake Valley, California. Finally, 1 hour and 57 minutes after launch, the confirmation was finally relayed to the ABMA officials in the form of the simple phrase, quote, "Goldstone has the bird," unquote. Radio signals were received from the Explorer satellite later than anticipated because it achieved a higher orbit than expected. Explorer was in an orbit with a perigee of 225 miles and an apogee of 1,594 miles, with an orbital period of 114.8 minutes. At 2 a.m. in Washington, a press conference was held featuring Wernher von Braun, William Pickering, and James Van Allen. Von Braun announced to the press, quote, "We have firmly established our foothold in space, and we will never give it up again," end quote. He, Pickering, and Van Allen held the satellite model over their heads for the cameras, and the image passed into history. Here's some of the audio from the press conference. The first clip is von Braun describing the rocket.
We have a total of 4 stages. The first stage is an elongated Redstone missile. You kindly show it, Joe. An elongated Redstone missile with extra long tanks and a special fuel combination, which burns for approximately 140 seconds, 145 seconds. After cutoff, immediately after cutoff, we separate the front portion of this missile the so-called instrument compartment from the tank section. And this instrument compartment is equipped with a special attitude control system, as we call it, that aligns this portion, including the spinning launcher in the nose, into an exactly horizontal position. Once this nose section with the spinning cluster configuration in the nose goes through the apex of the trajectory, the top stages are fired. And there are 3 solid rocket stages in the top. So it's a 4-stage vehicle.
Next, William Pickering responds to a question regarding the altitude achieved by the Explorer versus that of the Sputniks.
How does this altitude compare with the Sputniks?
This is somewhat greater than the altitude of either Sputnik 1 or Sputnik 2.
And finally, von Braun responds to the question, was there any life on board?
The question is, has any form of life been placed in the satellite? I think I could answer that one almost myself. Not intentionally.
Maybe we have a Florida cockroach inside, we don't know.
In Georgia, President Eisenhower was at his vacation home in Augusta on his first golf getaway since suffering a slight stroke around Thanksgiving. He interrupted an evening of bridge and his usual dinner hour for a briefing on launch preparations as they proceeded. The president was awakened when the rocket launched. He said cautiously, quote, "Let's not make too great a hullabaloo," end quote. Later, when it was confirmed that the satellite was in orbit, the president added, quote, "That's wonderful. I sure feel a lot better now," end quote. The next day, he took to the radio to announce the achievement. There was one other piece of business to finish. Even as the rocket climbed into the night, the satellite and the mission didn't have an officially announced public name. Missile 29 and Project Deal were uninspiring. General Medeiros liked the name Highball, whereas the Secretary of the Army suggested Top Kick. In the end, President Eisenhower approved the name Explorer, and that is what the Defense Department announced when the satellite achieved orbit. Explorer 1 made its final transmission on May 23, 1958. It entered Earth's atmosphere and burned up on March 31, 1970, after more than 58,000 orbits. 4 months after Sputnik, Explorer 1, also known as Satellite 1958 Alpha, became the first satellite sent aloft as part of the U.S. program for the International Geophysical Year of 1957 through 58. It also made the greatest discovery of the geophysical year. With only 1/6 the payload weight of Sputnik 1, Explorer scored a major scientific coup when its instruments sensed a pattern of radiation around the Earth, leading to the discovery of the now famous Van Allen belts. It is an interesting footnote on scientific history that Sputnik 1 could have made the discovery if it had installed simple instruments. Sputnik 2, in fact, did have the instruments, which operated properly and yielded data for 7 days, but the Soviet scientists failed to develop the data necessary to interpret the discovery. With the launch, America was now in the space race. Von Braun made the cover of Time magazine, and the nation enjoyed a moment of cheer. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.